Welcome pre-cal students to class today on this Wednesday the 23rd, April 23rd, 2014. Hope you guys are doing well. Hope you're ready to learn some math today. Let me get my cell phone out and turn it down here a little bit. All right, there we go. Oh, announcements. We will have a test on Monday, Matthew Caleb. So if you're not going to be able to make it, I would like to know no later than Sunday, please, if you would. So test on Monday, which means you'll have a review. Put RS, review sheet on Friday. There won't be a video on Friday, but there will be a review sheet emailed to you, and you can work on the review sheet if you want to, or you can wait until Monday. And then please stay on top of your integrity sheets. Whatever you do not have done when you arrive in class on Monday, you will not be able to do later. All right, let's continue on. You know me, guys, I go fast. So here we go. Let's quickly review what we studied yesterday. We studied something called direct variation. The model you need to be familiar with is y equals kx. You should be able to solve problems dealing with direct variation. We also studied inverse variation, and the model there that you want to be familiar with is y equals k over x. Okay? And you should be able to solve problems dealing with inverse variation. And then lastly, we talked about combined variation. I really didn't have any notes for you on that, just problems that we worked out. But I will remind you that the word jointly or joint variation, they vary jointly or they have joint variation, does mean direct variation. It's just more than one variable. Like if I said y varies jointly with x and z, then it would look like this. And so we talked about those yesterday. If anything I said is a little confusing, you will want to go back and watch parts of that video or the whole video, or make sure you understood your homework correctly or something, okay? All right, well, you know what? Another chapter wiped out, guys. Good job, and we're moving on to chapter 4 today. So I can hear your cheers all the way to my house. Chapter 4 is going to deal with exponential expressions and logarithmic expressions. You will enjoy these. They really are pretty cool. I think you'll like them. Now today we are going to look at inverse functions. Okay, inverse functions. And you might ask, well, how do inverse functions tie in with the two main topics of chapter 4, exponential expressions and logarithmic expressions? Well, good question. And simply put, an exponential expression is an inverse of a logarithm expression. Or you could say it the other way. A logarithm expression is an inverse of an exponential expression. Okay? Did I say that two different ways? I hope I did. Anyways, so they're inverses of each other. So it really only makes sense that we first study inverse functions and what they are before we get into studying exponential and logarithmic expressions. Your heading today is Inverse Functions, Lesson 4.1, and the date today, if you'd like to stay on top of that, is 4/23. All right, copy these in your notes if you would, please. Let's start off by looking at what inverse functions are. Now, the two equations below are inverses of each other. Now, Caleb, Matthew, don't worry yourself about saying, how did he get this? How did he know that? We'll get into that later, trust me, okay? And I did forget to put an X here and a Y here, so be sure and do that. But anyways, do you notice something about two equations that are inverses of each other? Notice in this equation the point 0, 1 exists, and notice over here the point 1, 0 exists. Notice over here the point 1, 3 exists. It satisfies this equation up here, and notice that the point 3, 1 over here satisfies this equation. 2, 5 is an ordered pair from this equation. 5, 2 is an ordered pair from this equation. 3, 7 is an ordered pair from this equation. And 7, 3 is an ordered pair that satisfies this equation. Okay? So I think, I'm kind of laughing, but you guys are pretty smart kids. I think you're seeing the pattern here. Do you see what inverse functions are? They are functions or equations, you can say either way, that have opposite domains and ranges. Okay, so whatever an ordered pair that satisfies this equation is, like 0, 1, in the inverse equation, 1, 0 will satisfy that equation. And again, don't worry about how you come up with these. I will teach you that actually today a little later. But for right now, I want you to understand this, okay? So let's continue on. With that last thought in mind, here are 4 ordered pairs from, I guess we'll just call it function h, okay? So function h has these ordered pairs: -8, 5, 4, -2, -7, 1, and 3.862. I want you to write 4 ordered pairs for the inverse of h. Let me show you how to write that. When you see h to the -1, you don't say h to the -1, you say inverse h, or the inverse of h, or h inverse is another way to say it. So that just simply means the inverse of h. And so the inverse of h would have these 4 ordered pairs. Now remember, these 4 ordered pairs up here are ordered pairs that go along with function what? Function h. And now these 4 ordered pairs here are going to be 4 ordered pairs that go with the inverse of function h, okay? And that's what this notation right here means. Well, -8, 5 is an ordered pair that satisfied h, so for the inverse of h it would be 5, -8. And 4, -2 satisfied function h, so -2, 4 would satisfy the inverse of h. -7, 1 was an ordered pair from h, so 1, -7 would be an ordered pair that we would get out of the inverse of h. And then 3.8 and 6.2 were an ordered pair for h, so we're going to turn those around, and an ordered pair that would satisfy the inverse of h is 6.2, 3.8. Notice you do not change the signs of any numbers. You don't do anything like that. You simply take the 2 numbers and you swap their places. That's all that you do. Isn't that simple? It really, really is. Now let's take this a step further. What if I gave you an equation? Could you find the inverse? Let's give it a shot. Here are the steps. Write these down. Step 1, everywhere there's an x, you put a y. And everywhere there's a y, you put an x. Isn't that simple? And then step 2, solve the equation for y. Solve the equation for y. Okay? So really, this is not too difficult. Let's try a couple of these. Okay? So that's it. Pretty simple. Let's try this. Here we go. All right. Let's go ahead and start off with this equation right here. I want you to find the inverse of this equation right here. Are you ready? Here we go. Step 1, everywhere there's an x, you put a y, and everywhere there's a y, you put an x. There we go. Now, in this problem here, I'd like to point out to you, everywhere there was a y, we put an x, and everywhere there was an x, we put a y. Now, step 2 says solve for y, and I intentionally gave you a problem like this where you really couldn't solve for y. Now you say, well, Mr. Earhart, we could try to. Sure, you could. We have all of our y terms on one side and our non-y terms on the other side. So you could factor out a y. And then in order to get this y here by itself, you could divide both sides by y minus 5, like this. And divide the other side by y minus 5. And that looks pretty good. These would cancel out. But the only problem is notice that on the left side over here, on the left side, you have an actual y over here, and that y would be right here. And anytime you're solving for a variable, you want the only y to be over here. So this would be one of the problems where I would not expect you to solve for y, because it's really, really basically impossible to do. Now I will say this, I think you could solve this by completing the square. Wouldn't that be fun? Yes, I'm being sarcastic. And if we had a lot of time, I would do that for you, but there's just no need. So in this case here, we're totally good. This equation here is an inverse of this equation right here. Okay? All right. Now let's take a look at this equation over here. Here's your y. I'm going to put an x. Here's your x. I'm going to put a y. Now let's get y by itself. Bring the 8 over and make it positive. So now I have x plus 8 equals 5y. And now we're going to divide every term by 5. But don't forget there's a 1 in front of the x. So 1 divided by 5 is 1/5 x. 8 divided by 5 is 8/5. And then 5y divided by 5 like this, your 5's would cancel, just leaving you with y. Now, there are a couple things you need to see. First of all, this equation here and this equation here are inverses of each other. And I do want you guys, Caleb, Matthew, to get y by itself when you can. And most of the time you'll be able to. Now, I think the back of the book in your homework leaves their answers, all of them, like this here. And I want you to get y by itself when you can. Now, there's a notation I really need you guys to get used to, okay? So please watch carefully. Watch carefully, guys. This is very important, okay? Now, look. If this is the equation you started with right here, the one that you get out, you really want to put y to the -1. That means y inverse, or the inverse of y. So if you're, and usually you put the y on the left side, so it would be y inverse equals 1/5 x plus 8/5. Now I don't care if you leave it like this or this. I'm just trying to teach you proper symbolism. So in this case, you would not say y to the -1. You would say the inverse of y equals 1/5 x plus 8/5, or y inverse equals 1/5 x plus 8/5. And what you're saying is this equation here is the inverse of this equation up here. Something else you need to be ready for, guys. Instead of having a y here, what if this would have said f of x, like that? Okay, well, that's no big deal. You look at this like it's a y, so you put an x here, you put your y over here. That's no big deal. And then you solve for y. All of that is fine. I've not really changed anything, but here's the key. When you're all done solving the equation, if the original problem was in function notation f of x, then right here for your answer, you write your inverse function like this. And you don't say f to the -1 of x. You say f inverse of x, or you can just say inverse f of x. But either way, this notation here just simply means that this equation here is the inverse of this equation up here. Okay? So make sure you're familiar with that and make sure you know how to do that. Now, I'd like to throw kind of a crazy comment at you and then show you what I mean. Here's the comment. You might want to write this down. Every equation does have an inverse equation. However, not every function has an inverse, keyword here, function. Let me give you an example below and show you what I mean, okay? All right. Let's say we had a graph and we graphed, let's say we had a function and we graphed the function and it looked like this, okay? There we go. Now, we understand that that is a function, and by the way, students, listen to me, we do know that that's a function because remember the vertical line test? Everywhere you draw a vertical line, any vertical line that you draw will only touch or intersect the graph in one place. Remember we studied that, it's called the vertical line test. Now, if I wrote the inverse of this function, let's think about it. This point here is -3, 4, so the opposite of that would be 4, -3 right here, and I should change colors. Now just watch what happens. Here I have 0, 1, so I'm going to go with 1, 0. Then over here I have 3, 4, so I'm going to go with 4, 3. So if you sketch that, if you sketch the inverse graph, and that was easy to do, was it not, students? I should not have lost you there. Remember, we just finished studying a little bit ago that anytime you have an ordered pair, to find the inverse of that ordered pair, you just swap it around. You swap the x and the y. So I took this point, swapped it around, plotted it down here, took this point, swapped it around, plotted it here, took this point, swapped the x and the y, and plotted it right here. And then I sketched my graph. So the green graph is the inverse graph of the red graph. However, I have a question for you men. Is the green graph a function? Well, think of your vertical line test, guys. Look. Is Is that green graph a function? No, it is not, because I can draw vertical lines that intersect the graph in more than one place. So, Mr. Earhart, what are you trying to show us? Here's what I'm trying to show you, and then you can pause the video and take notes however you want to. I'm trying to show you that just because a graph is a function, it doesn't mean when you graph its inverse that the inverse will be a function. And that's why I said this here. Not every function has an inverse function. And I just gave you an example right here. Here's a function, but when I drew its inverse, it wasn't a function. This green graph is not a function. Now, if you're not using the word function, if you're using the word equation, then no problem, because every equation does have an inverse equation. That's fine. I have no problem with that. But if you have a function, do not assume that it has an inverse function, because the inverse equation of that function might not be a function. It might look something like this. Okay, so study that and make sure you understand that. Now, when a function does have an inverse function, we say that the function is 1-to-1. When a function does have an inverse function, we say that the function is 1-to-1. Let's go back a page here. This red function, does it have an inverse function? No, it does not. So this red graph right here is not, it is not a 1-to-1 function. It is not. Now, if this red graph would have had an inverse function, then we would say this red graph is a 1-to-1 function. Okay? All right. Now let's continue on. Okay, guys, let's continue on. Now, there is a way to use a horizontal line to see if a graphed function has an inverse function. And you're used to the vertical line test, right? Well, this test is called the horizontal line test. Let me show you how this works. Please take some good notes. Now, let's go back to our good old graph we had a little bit ago. Okay, this graph right here. Okay? Now, when I graphed the inverse of that, it looks something like this, correct? So notice that when you flipped it, notice that vertical lines intersected the graph in more than one place. Well, what if I took the original graph, this one here, this original graph, and I said, okay, I wonder if this graph, the function of this graph, has an inverse function. And there's a fast way to check and see. It's called the horizontal line test. If there's any place in this red graph that you can draw a horizontal line in which that horizontal line touches the graph in more than one place, then this graph, this red graph, is not a 1-to-1 function. Thus, it does not have an inverse function. Let me say that again. If you want to know if a graph has an inverse function, if there's you use the horizontal line test, and what this means is if there's anywhere you can draw this horizontal line, anywhere, and that horizontal line intersects the graph in more than one place, then this red function, this red graph, the function of this graph is not a 1-to-1 function. Thus, this red graph, the function of this red graph, does not have an inverse function. It does not. And so that's kind of a quick way to check to see if a graphed function has an inverse function. Okay? Now, moving on, and we're done. In closing today, I would like for you to write the inverse of this graph. So I want to show you something here. They've given us a red graph, and here it is. I'm going to highlight it in green. Here's the red graph, okay? And they want us to graph the inverse of that. Okay, no problem. If an ordered pair is 6, -3, then I know one of the ordered pairs that exists would be -3, 6, which is about right here. And then if on your red graph we have -4, 2, then on the inverse graph we would have 2, -4. I just swapped these two numbers around and plotted the point right here, and then I just simply swapped those two numbers around and I plotted the point right there. Not too bad. Now, let's take a look at this point here. 1, 3 is on the red graph, so the inverse graph would have a point at 3, 1. And then 2, 5 is on the red graph, so 5, 2 would be on the inverse graph, okay? And with that in mind, let's go ahead and sketch the graph now quickly, okay? So there we go. And there we go. And there we go. Not too bad, okay? Now, I'd like to show you something that's really neat here. Now here's what I want to show you guys. The reason, Mr. Earhart, why did they draw this dotted line down the middle of the graph? Well, I'm glad you asked, okay? Anytime you have a graph and then you graph its inverse on the same coordinate plane, if you were to draw a dotted line y equals x, and by the way, that's if you were to graph y equals x, which you guys know how to do, that's a linear equation, you would get this dotted line right here. And why is that such a big deal? Well, because here's why. Another way to know that you have an inverse graph is, see this point here? See its inverse point right here? Notice how they're both the same distance from the dotted line. See this point here? And see its inverse point over here? Notice how those 2 points are the same distance from the dotted line if you were to draw a perpendicular line. See this point here and its inverse point? This point here, if you were to draw a perpendicular line to the dotted line, that distance there is the same distance as this here. And then lastly, see this point here and its inverse point here. If you were to draw a straight line like this, perpendicular to the dotted line, and then draw a perpendicular line to the dotted line, those 2 distances would be the same. And that's always true when you have inverse graphs, okay? And so that's another way to kind of recognize inverse graphs, okay? All right, that's it for today. I hope this has been decently easy to understand. Let's go ahead and get started on your homework. You're doing today page 356, 1, 3, 5 through 10 all, 25 through 31 odd, and then 67, 69, and 71. The homework video tonight is pretty short, so I don't think this will be too difficult for you. And if you have any questions, men, as always, don't hesitate to call or email.